time for a pop quiz. QED.
Hello everyone, welcome on in. My name is Ben Center. We're here for the Summer of Machine Learning. We are going to do a little classification today, I think. I think that's the plan of attack for today. So I'm just waiting on some ads to roll through. And we'll get the party started. Yeah, I'm sorry about EnigmaBot. EnigmaBot has died. And all of the commands that EnigmaBot normally would use are dead. Anything that starts, I think EnigmaBot was a $sign. Anything with the exclamation mark should work. Yeah, some of these should be okay. Stream Summer Sale started today and you bought a bunch of stuff. What? What does that mean? Oh, Steam Summer Sale. Oh, I was like, Stream Summer? I was like, what? What's Stream Summer Sale? I was getting excited. I was like, oh, sweet. Maybe I'll get a discount on all the people that I follow. I did a bunch of Steam purchases a while back for some games that I'm hoping to play in the near future. Let's see, let's redo that. Okay, I've sent my message to Enigma. For those of you that might be new to the machine learning sessions that we're running on Friday, there is a section inside of our Discord. So under the machine learning heading, I have the resources here. So if you want to kind of follow along with some resources, and I know Addy also posted some potential YouTube links as well that might be beneficial for us. Mostly because, I mean, personally, I don't like reading all the time, so just give me a second here to get my everything looking good. Okay, that's how I want that to be. Perfect. NB selling math 50% off. Don't tell anyone. Don't say anything. Ooh, you bought the DLC for Outer Wilds? Ooh, I've heard it's quite good. I've heard it's quite good. A little scary, too, actually. Now let me turn that down just a touch because it is going to probably distract me slightly. So the goal today is I want to read through Chapter 3 of Reese. We've had some questions posted into Discord as well. So I think it's just under the general chat. There's been a little bit of talk about some stuff in linear regression. Reese does classification first, so we'll take a look at classification. Actually, let's take a look at when regression actually happens. When does regression happen in Reese? As part 3. Yeah, so I want to read through K nearest neighbors. We could actually probably bump over into linear regression afterwards, because I know that the James textbook, I'm still trying to kind of work my way through a little bit of Chapter 2, but they go into linear regression right away. So I feel like, I don't know how much we're going to need linear regression for classification. That's a little bit unknown to me. But I wouldn't be opposed if someone has some ideas on how to help QK answer some of these questions. You're more than welcome to post in the general. You can start a thread as well if you want to work through some of those questions. Yes, Martin is correct. So yeah, to scroll up to the top under channels and roles, you can give yourself the online classes role up at the very top, mouse. And then that way, what I do is I always, anytime that there's an online class, I just kind of encourage like the staff or the instructors here to have that tag, and that way it doesn't bog down stuff that people don't necessarily want to see. But that should open up all of the current classes and probably the past classes as well. You have them all too? What? Well, let's look. Do you... But not that specific one? That's weird. Here are the perms, friends. Online classes have the perms to view. Invite. We can invite you. Yeah, as long as you have the online classes role, you should have access to that. So that's questionable. I mean, I can add you as a specific individual. Are you... Wait, Mouse, are you part of the elements? Okay, what's this? What's this Imgur? What is this? Yeah, it's in the ML General. Oh, you want the resources. I see. Okay, so you're unable to see the forum post, is what you're saying. What are my permissions in here? Online classes should be able to view, create posts. So with that role, you should be able to get in there. It is a pinned message, so I don't know if that makes it a bit trickier to find. I could unpin it.
Why did you even rope me into this? Because he roped me into this. Well, him over there, he roped me into this. Well, he roped me into this. What about me? He roped me into this. Well, that one over there roped me into this. Well, he roped me into this.
Yeah, I don't know. Some Discord's weird to me sometimes. And Discord on mobile has been super janky with me the last little while. Oh, Phobos invited you. That's super sweet. Hi, Deezy. Welcome in. Deezy, how did you get second? Did someone get first?
Zeta, welcome. Remember, gratitude is just another function in the equation of life. Stay sharp.
Okay, so let's talk about K nearest neighbors. Classifying based on similarities with K nearest neighbors. I like this. This is probably the most important chapter in the entire book. Yeah, did someone actually claim first at all? No one claimed first. Okay, so something just broke. That's fun. That means we'll get more than 1 second and 1/3 this stream. Dan. There you go. You get a duck. Press the follow button if you want that to show up on the left. What does that mean? You have to follow the thread? That's weird. Yeah, I guess that way it'll pop up down here, right? And you can always find it quickly. Oh, Discord. Penda, yes, I've seen it all. Seen it all. Broken streamer.button has only been 10 minutes. Okay, how is this the most important chapter in the entire book? Yeah, I need to do some stats too. I'm hoping we'll be able to do a little bit of stats today. It might not be in this particular book. I think this book tends to be a bit more coding heavy, but I think in the James book we might be able to do a little bit of stats today. Except for math, I'm blind to math. Well, come and hang out and be unblind. Whoa, that's crazy. We're going to see the K-nearest neighbors algorithm, and we're going to use it to classify potential diabetes patients. Okay, cool. In addition, I'm going to use the Canon algorithm to teach some essential concepts in machine learning that we will rely on for the rest of the book. Okay, interesting. By the end of this chapter, not only will you understand and be able to use KNN to make classification models, but you'll be able to validate its performance and tune it to improve its performance as much as possible. I'm cool with that. I'm down with that. Once the model is built, you'll learn how to pass new unseen data into it and get the data's predicted classes. Okay, so this is a problem of... we're going to look... I'm assuming we're going to have a bunch of data. We're going to be looking at one specific variable. Oh, thank you very much for the follow, Mouse. You suddenly lost your glasses and you can't see math anymore. What? It depends what you need to do. Like, I use the Casio FX Plus calculator. The old models look like this. The new updated models are black. But I love these models because it has built-in stat modes. So I can go in and I can, for basic stats, I can program in one variable stats or a linear regression. It has some exponential logarithmic, exponential power functions, reciprocal functions. So you can build in a bunch of stuff. For stats, it also has, if I remember, it has different distributions, if I remember, as well. Our matrix. Yeah, so it has different distributions. It has like the normal distribution automatically built in. So if you need, instead of looking at a table for the normal distribution, you can just use a calculator. That has the inverse normal built in, has the binomial and the Poisson distributions built in as well. So I really like this calculator. When I used to teach introductory statistics, this is the calculator I would tell my students to purchase. And it's also nice for, like, it's got equation solvers. It can do integration for you, like numerical integration really quickly. So it's pretty nice. I quite enjoy it for what I need it. And then anything higher than that, I just go to like Maple or R, and they can usually. Yeah, I'll be using R. I'm fairly comfortable with the lingo in R. Fairly comfortable. I'm not like super great at it, but yeah, we use R in our data science program, but I know there's data science programs that use Python too. R has a pretty steep learning curve, but I mean, once you get, have you learned a language before? It's a pretty steep learning curve, but if you've learned a language before, it's not terrible. It just doesn't follow the usual kinds of syntax that you would expect things to. Okay, yeah. If you have those under your belt, it's going to be a pain in the ass, but you'll be able to pick it up pretty fast. Oh, I'll introduce you to the extremely powerful MLR package, which contains a mouth-watering number of machine learning algorithms. Okay. A mouth-watering number. Wow. That is that's kind of kinky. What's the K nearest neighbors algorithm? I think the simple things in life are best. Playing frisbee in the park, walking my dog, playing board games with my family, and using the KNN algorithm. Bro. Bro. What? Oh, you're up to 15K. Yeah, if you could get the VIP redeem, that's true. Or you could spin the wheel and try to get it on discount. It depends on what game you want to play. Okay, so they're saying it's very simplistic, basically, right? They're saying, I like the simple things in life. KNN is one of the simple things in life, apparently. The simplest machine learning algorithm, and this is one of the reasons I like it so much. Okay. KNN can provide surprisingly good classification performance, and its simplicity makes it easy to interpret. Okay, that's good. Right, okay, so this is going to be a supervised learning algorithm. That's what I was trying to figure out. Those are the things we learned last week. So we have the supervised learning algorithms where we kind of know the outcome, right, of our input variables. And we have the unsupervised learning algorithms that don't know the output. So in this case, we happen to know the output, and we're, I guess, using the known outputs to cluster based on certain characteristics. What is this book? This book is so bizarre. How does KNN learn? Well, I'm going to use snakes to help me explain. What? I'm from the UK, where some people are surprised to learn we have a few native species of snake. Okay? Two examples are the grass snake and the adder, which is the only venomous snake in the UK. But we also have a cute limbless reptile called a slow worm. Ew, that sounds gross. Slow worm. What's a slow worm? It kind of looks like a snake, actually. I was expecting to be more worm-like, I'm not gonna lie. It looks like a snake. That's a snake. You can't tell me that's not a snake. Look how cute that thing is. That's a snake. Okay, so we're going to work for conservation. We're going to count the number of grass snakes, adders, and slow worms in a woodland. Your job is to build a model that allows you to quickly classify reptiles you find into one of these three classes. Okay, so classes we can think of like the bins, our output bins. And it's going to be the type of snake, right, or the type of reptile. I guess that's going to be what we're classifying. When you find one of these animals, you only have enough time to rapidly estimate its length and some measure of how aggressive it is towards you before it slithers away. Funding is very scarce for your project. True. That hits hard. That hits deep. Oh my gosh, that's funny. I know, what a name, Ryan, right? This could be a monster in games like Diablo or something. Totally. Reptile Expert helps you manually classify the observations, but you decide to build a KNN classifier to help you quickly classify future specimens. Okay, look at the plot of the data before classification in figure 3.1. Each of our cases is plotted against body length and aggression. Okay, so there's two measures. They look like continuous measures. And the species identified by your expert is indicated by the shape. Okay. You go into the woodland again and collect data from 3 new specimens, which are shown as the 3 X's. Okay, so body length and aggression. Right, so we get this kind of cluster down here in yellow that seems to have tends to have shorter body length and milder aggression. If it's mildly aggressive but longer, it's a grass snake. And if it's long and aggressive, it's the adder. All right, chat, which one of you are long and aggressive? Anyway, we can describe the KNN algorithm and other machine learning algorithms in terms of 2 phases, the training phase and the prediction phase. Okay, so the training phase is probably inputting the original data, I assume, right? Yo, how's it going? Welcome on in, ads. How's your day been? We're doing a little machine learning. I'm learning about classification today. We're talking about snakes. We're talking about long and aggressive snakes today. Hopefully you're into long and aggressive snakes. So the training phase consists of sorting the data. This is unusual. What? The training phase of the KNN algorithm consists only of sorting the data. Huh? Hi Rex, welcome in. This is unusual among machine learning algorithms, and it means that most of the computation is done during the prediction phase. Well, that's cute. That was like a goldfish mixed with candy corn? What was that called? A candy corridoris. That can't be true. Bad news, you died to the snake bite because your KNN program took too long, damn. Yes, you're right, Martin. It has the normal people humor and not the weird niche math humor. I kind of like it for that, I'm not gonna lie. It's also like very dry, like it feels like very dry British humor too, which I really appreciate as a dad. Sorry, no, I'm not a dad. As a dad joke enthusiast, I should clarify. During the prediction phase, the KNN algorithm calculates the distance between each new unlabeled case and all the labeled cases. How does it initiate, I guess, would be my question. What's the initiation phase? It must have to choose K things to start an algorithm, right? Then it goes through a process of iterative distance thinginess. And when I say distance, I mean their nearness in terms of the aggression and body length variables, not how far away in the woods you found them. That's not even funny. You go away. The distance metric. Okay, so they're using Euclidean because these are two continuous variables. Right. And they're using straight line distance between any 2 points on a plot. Oh, wait. How does it get the... Oh, I'm an idiot. There's no initiation. So just plotting it is the initiation phase. Okay, and I understand what they're saying now. So all we're doing... Yeah, I see. So we're plotting in the known 3 things, like so, and then we're adding in the new data that we don't actually know about, and it's going to calculate all these distances. They're showing us an Euclidean metric to make things simpler, and it's going to calculate the distance to all of the known data points and then make a decision. Okay, that makes sense. Got it. So the first step in the KNN algorithm, calculating distance. The lines represent the distance between one of the unlabeled cases, yes, and all of the labeled cases. That makes sense. So they've only done this in 2 dimensions. I assume that, if we have a bunch of continuous variables, we should be able to do this in n dimensions. Now, I would be curious what their take is on how to deal with stuff that's not continuous. So what if I have discrete variables? How does that work? I'd be kind of curious to know about that. I know there are other algorithms that we might be able to use. But anyway, let's keep reading. So next, for each unlabeled case, the algorithm ranks the neighbors from nearest to furthest. Okay. I see. So 1, 2, 3, they're putting numbers here. So 1, 2, 3, 4, 5, 6, 7. Where's 8? Oh, 8 is a purple one. 9, 10. Okay, so this is where the K comes in then. Okay. I see. So now we just play a voting game, don't we? We just say, okay, well, how many of the 5 nearest neighbors are green? Right? And then if green wins that vote, then we label X green. That must be the way this works. This surprisingly makes a lot of sense. We're not really doing any math right now. I'm just kind of logically trying to figure out what the heck's going on. Oh, hey Raptor, how's it going? Any Oiler folks here? Yeah, you got a fish. Good for you, Rex. Good for you. That's a good fish, too, wasn't it? It was worth 217 gold. Damn. So the algorithm identifies k labeled cases, neighbors nearest each unlabeled case. K is an integer specified by us. They're going to tell us how to select it in 3.1. In other words, find the k labeled cases that are most similar. Finally, each one of the k nearest neighbors casts vote. Yeah, okay. So cases votes on which the class the unlabeled data belongs in based on the nearest neighbor's own class. That is a horrible sentence, but I know what they're talking about. In other words, whatever class most of the k nearest neighbors belong to is what the unlabeled case is classified as. Yes, okay, that makes sense. Because all of its computation is done during the prediction phase, KNN is said to be a lazy learner. It's just like me. A very lazy learner. Just tell me all the shit you want me to learn. I don't need to read it. Let's work through figure... Give me a video. I'll just watch a video. Let's work through figure 3.4 and see this in practice. When we set k equal to 1, the algorithm finds the single labeled case that's most similar. Each of the unlabeled reptiles is closest to a member of the grass snake, which is the green ones. So we're looking at these 3 X's. We're finding one neighbor that's the closest and labeling the X's as that one thing. So they've given us some examples of 3 nearest neighbors as well. So again, the X's, so we're finding our 3 nearest neighbors. Obviously the one at the bottom becomes green because its 3 neighbors are all green. This one becomes purple because 2 votes are cast for purple, 1's cast for green, 2 cast for yellow, 1 cast for green. So this one is overall yellow. So you can see that, yeah, there definitely are some changes as k changes, right? So when k was 1, everything turned green. When k is 3, we have 1 new of each reptile variety. And when we use 5 nearest neighbors, 2 become green, 1 stays yellow. So things do change as k changes. Slow worm. It's just not very long and not very aggressive. I can't handle this today. When we say k equals to 3k, so we've already looked at the 5 case. Yeah. Wait, the KNN algorithm can actually be used for both classification and regression problems? That's interesting. Oh, instead of taking the majority class vote, the algorithm finds the mean or median of the nearest neighbor's values. Interesting. Talking to Misha. How's Misha doing? Martin, what do you mean by can we not just put it at 0 and 1? It's also not very practical as you need to store the training data. Oh, about the discrete stuff. Yeah, I guess if we can turn it into... Yeah, if we can store it as numerical, like... If we can store it as numerical discrete, if it's like male, female or something like that. Yeah. I see. So what you would do with different... if you had different factors, I guess, is you would just convert them to numeric. If they had an order to them, maybe. I guess even if they didn't have an order, you could still theoretically do that. And then I know there are some other algorithms other than the Euclidean, or other distances other than the Euclidean distance, then maybe we could utilize there. Now, Pui, are you talking about the algorithm in general? So for like KNN in general, I could see that it would become very, very costly if all of the training data had to, like if you had a crap ton of training data, I could see that being very costly, like to calculate all of the distances for each of our new input points would take a lot of processing power. Is that what you mean? That's kind of how I'm interpreting your statement, but if you want to add some clarity, I'd be happy to read it. So what happens if the vote is tied? Choose K. Choose a K value that's odd. That's the answer to this question. Choose a different value of K. Add a small amount of noise. Consider using... Wait. It may happen that the K nearest neighbors belong to different classes. Oh, that all of the K nearest neighbors belong to different classes. Yeah, I guess that could happen, right? And that the vote results in the tie. What happens in this situation? Well, one way we can avoid this in a two-class classification problem is to ensure we pick odd number of K. Yeah. So it would be dependent on how many cases you have, right? Like, let's say I had 5 different cases, then would I pick K is equal to 7? I'd probably pick, like, the next highest odd number for my K value, and that would always deal with the tie vote problem. Is to decrease K until a majority vote can be won. Oh, okay, so that's another way to do it. But this doesn't help if an unlabeled case is equidistant between its two nearest neighbors. Instead, a more common approach is to randomly assign cases with no majority vote to one of the classes. Oh, interesting. In practice, the proportion of cases that have ties like this, I would assume, would be very small. Yep, so this has limited impact. Especially, I suppose, especially if you have a really large set of data, this probably wouldn't affect it too much. But if you have many ties, yeah, choose a different value K, add a small amount of noise. I'm curious to know what that means. Considering using a different algorithm. Okay. Whoa, building our first KNN model. Imagine you're working in a hospital and are trying to improve the diagnosis of patients with diabetes. Okay. Yeah. I'm there. Just call me Dr. Brian. You collect diagnostic data. Oh, we could pretend to be Dr. Zach today. You collect diagnostic data over a few months from suspected diabetes patients and record whether they were diagnosed as healthy, chemically diabetic, huh? Or overtly diabetic. What does chemically diabetic mean? You would like to use the KNN algorithm to train a model that can predict which of these classes a new patient will belong to so that diagnoses can be improved. This is a 3-class classification problem, just like the snake data. We're going to start with a simple, naive way of building a KNN model and then gradually improve it through the rest of the chapter. First things first, let's install the MLR package. Yeah, let's do that. Hey fam, how's it going? Wiggling the points a wiggling the points a little bit, wiggling the snakes a little bit. Should we wiggle the small unaggressive snake or the large aggressive snake? So, I'll stop making snake jokes eventually, I promise. What was this? Oh yeah, I don't need that. I probably don't need any of this either. Let's just clear the whole workspace. Okay, what are we doing? I have no idea if I actually have the MLR package, so yeah, let's install .packages MLR. Now it says dependencies equals true. What does that mean? Oh, all the dependent packages. Oops. Oh, you son of a gun. There we go. And then they want me to open up the MLR and the tidyverse libraries. Okay, so let's do that after. This is probably like the hardest part of coding, right? Is just waiting for all of your libraries to be downloaded. Happy Friday, by the way. Look at all of these packages being downloaded. Oh my god. At MIT, they also teach k-medioids as an alternative to k-means. In k-medioids, the center of a cluster is determined as a median, and one advantage is that the center of a cluster is actually one of the data points. Whereas in k-means, the center of a cluster is an average, the centroid, yeah. That is usually in itself not a data point. Yeah, that's a really good point. I have heard of that as well. Yeah, so we're working on k nearest neighbors, which I suspect we'll learn about k-means eventually. I think k-means is slightly different from k-n-n, right? Slightly different in its approach for how it classifies new information. Because I'm under the impression that k-means can kind of change over time, right? You can kind of watch the shift over time, where k-n-n, I think it already knows all the information that it needs, and then when you go to input a new piece of data, it's actually doing a calculation and then classifying it. Yeah. Hola, friends! ¿Cómo estás, Caler? Yeah, okay, that's the word. You guys will get me using those words eventually. K-means is unsupervised, gotcha. Why are people trying to call me? Go away. How are you doing, Sasha? Holy moly, this is taking forever. I guess I can type out some other stuff. So what are we going to need? We're going to actually need the MLR library, and we're going to need the tidyverse. I should have tidyverse already figured out. I guess we can read while that's warning. Installing the MLR package could take several minutes. Yes, that's totally correct. Loading and exploring the diabetes dataset. Now let's load some data built into the mclust package. Convert it into a tibble and explore it a little. Okay, let's actually open it up and look at it ourselves. So diabetes package mclust. So while that's doing its thing, I think I can probably open up stuff. So I assume it's going into the mclust package, grabbing something called diabetes, and it looks like it might save it as something. So maybe it's just extracting the data. Let's take a look. Does it bring it into... hello? Oh, I see. It's still installing stuff. Me when I read any math book? What? Oh no. About to start an OOT rando with a friend? Nice. Nice. Good luck. The best. I haven't done an OOT rando in like 2 weeks. I'm gonna practice. But I'm hoping in July I can have a pretty consistent schedule. I think I'm just going to start doing what I'm doing for machine learning and just being like, yo, on Thursdays, I'm going to play Zelda. On Fridays, we're going to do machine learning. On Mondays, I have a new game called Blueprints that I want to start playing. I've seen a little bit of gameplay of Blueprints and it looks quite good. That's going to be addiction for real? Okay. That's good to know. So I'll have to do that. Do you think I'll have to do it more than one night a week? People have told me I'm going to need like a little like notebook to like write shit down in. In the meantime, let's take a look at what Martin what did you clip here, Mr. Martin? This surprisingly makes a lot of this surprisingly makes a lot of what this surprisingly makes a lot of sense. Is that what you clipped for us? Sometimes it works. Sometimes things make sense. Sometimes they. I should have done this. I didn't realize we were going to be installing a whole package. Here, while we're waiting, let's see if I can. What do I have in here? Run. Oh, that reminds me. I need to get my generative AI music working again too, don't I? Oh my gosh. This is more than a couple minutes. Okay, anyway, well, let's do a little bit of reading, I guess. So we have a table with 145 cases and 4 variables. The class factor shows that 76 of the cases were non-diabetic, 36 were chemically... Oh, I wanted to look that up. What does chemically diabetic mean? What does that mean? The definition of chemical diabetes. Overt diabetes is the most advanced stage, characterized by elevated fasting blood glucose concentration and classical symptoms. The stage is divided into ketotic and non-ketotic. Is that how I pronounce that word? Preceding overt diabetes is the latent diabetic stage. Okay, so it's where you have symptoms. No symptoms, but you're showing signs. No symptoms of diabetes, but demonstrable abnormality of oral or intravenous glucose tolerance. Gotcha. Okay, that makes sense. Okay, so either you don't have it, you're on the way to having it, or it's expressing itself completely. The other 3 variables are continuous measures, which is good. We'll be able to use Euclidean distance of the level of blood glucose and insulin after a glucose tolerance test. Okay, so glucose and insulin, measure that. And the steady state level of blood glucose. Steady state PG. What does the P stand for? Steady state PG? Parts of glucose? The G probably stands for glucose. Okay. Okay, so we have a class variable that measures these 3 classes. The summary is going to give us the summary statistics. So yeah, it gives us our quartiles, our mean, median, min, and max. And this looks like it's every 145 individuals combined, right? But it will give us at least a baseline of... It would be probably better if we went in and actually looked at some stuff individually, and we could kind of compare these averages, right, to see if these averages differ between the groups, because this is just a big glob of information that's probably not as helpful as it could be. Hello? Are you still going? You're still going! Oh my gosh. Oh, plasma glucose. That makes sense. Yeah, okay. yeah. Long Snake was definitely auto-modded. Yeah. It's now permitted, though. If you want to talk about long snakes, you're more than welcome to. Long and aggressive snakes. I thought for sure there'd be a long snake joke in there. Did this die? Nope, we're good. The aggressive part is essential, it's true, yes. Long and aggressive. Two very important adjectives. Okay, so I still can't play around with the data yet because ours is loading a whole bunch of stuff. But we'll come back and we'll do this. Because I do want to I want to look at some of this stuff a little bit in a little bit more detail. And just remind myself how to do some of this stuff. To show how these variables are related, they're plotted against each other in figure 3.5. The code to generate the plots is 3.2. Cool. So they did insulin, so glucose versus insulin for the three groups. SSPG versus insulin for the three groups, and then SSPG versus glucose. Ooh, so you can really see the yellow. So yellow is overt. Just, these two are so tightly clustered, and then yellow is just all over the map. Look at that, right? Just a very clear. So what's this saying? So as glucose levels rise, those with overt diabetes have insulin levels that also rise dramatically. Does that seem right? I thought diabetes was inability to produce insulin. And this is saying that the steady state glucose levels. Oh, I see. So it may be like insulin tends to stick around even though our steady state's small. And what's this one saying? This one's saying the steady state. So it's almost as if it's not, the insulin is being produced, but it's not breaking down the glucose. Right? Because our glucose levels are just crazy. Right? And our insulin levels are high at the steady state. .3D graphs that are easy to read because everyone is. Imagine if we got like 5D graphs that were easy to read and using VR. That would be pretty cool. That's only one of the types. The other type is the body got used to insulin, so the insulin doesn't really reduce glucose. You challenged a slow worm to a duel in order to measure how aggressive it is? Oh god. Apparently they're not very aggressive. Apparently they are non-snakes that are short and non-aggressive. Apparently. Let's just, I want to just make sure that this makes sense. There are two different types of diabetes, right? Now, does this textbook tell us what kind of diabetes we're working with, or is it just diabetes? I don't know if they told us what type of diabetes it was, right? Just diabetes. That's all we know. It's just diabetes. So it's unclear if it's type 1 or type 2. Add your data point to the graph. Shut up. Okay, so type 1 cannot make any insulin. I see. So type 2, your body is unable to make enough insulin, or the insulin you make doesn't work properly. Okay, so it's just, yeah, so that's all I wanted, Martin. I just wanted to remind myself which was type 1 and type 2. We must really be talking about type 2 diabetes here, because we're making a crap ton of insulin by the looks of it, and it's not bringing the glucose levels down. So this makes sense now. I just wanted to make sure that I understood what I was seeing. Okay, so that's the information for us to plot. How are we doing in R? Are we getting anywhere? Now, I don't know if you can see that. It feels super tiny, But if you're working through R and you have that data loaded, you can actually see the different classes, the glucose, insulin, SSPG levels. Cool, okay. So they have all the normal individuals. Is it mixed up? It is mixed up. Okay, so it's not necessarily sorted in any particular order. Oh no, overts all seem to be at the bottom. And chemical and normal seem to be just kind of mixed up. Okay, cool. Let's go back and actually make these plots. Okay, so we brought the data in. It's asking us then to convert this into a tibble. So I wonder if it comes in as a data frame? Yeah, so it comes in as a data frame, and this textbook is just asking us to convert it to diabetes. Tib is what they want to call it. The arrow is the assignment syntax. So as tibble. That seems fine. As tibble could not... What? Did I spell it wrong? Oh, I didn't add the... I didn't actually open up these... My bad. I forgot to open up the tidyverse. Whoops. Dependencies. Okay, there we go. So now it's as a tibble. We've already looked at the summary. I don't particularly care. That's just more information about what it looks like, which we've already looked at. So I'm fine with that. Okay, let's just make sure that we're cool with these plots. And I think just for sake of time, I'm just going to go ahead. We can actually just copy and paste these in, I think. So all it's doing is taking the tibble. This is the aesthetic. So the aesthetic is kind of defining how we want the original plots to look like. So this one's plotting glucose, insulin, with the color being the class. It's adding in points, and the theme is just a simple black and white theme. I guess a zoom is what we do here. So nothing super crazy here. But if we want to take a look at that data in R, I guess this is how we do it. So we can build these in case we need to refer back to them for anything. But we've already kind of talked a little bit about those plots. So let's see. Looking at the data, we can see that there are differences in the continuous variables among the three classes. So let's build a KNN classifier that we can use to predict diabetes status for measurements of future patients. Exercise 1. Reproduce the plot of glucose versus insulin shown in figure 3.5, but use shapes rather than colors to indicate which class each belongs to. Once you've done this, modify your code to represent the classes using shape and color. So, wait, which one do they want me to do that for? Glucose versus insulin? So that's going to be this first one. Wouldn't I... So if I take this and I fiddle around with it down here, I need shape to be the class. What's the code for that, though? Is it just shape? Yeah, so that converts the classes into shapes. I don't know how to get the color in there, though. Do I just add the color in there afterwards? And also, I mean, if I was making this for a report, I'd probably want to make these a little bit bigger so I could see them a bit easier as well. Can I do this? Well, it might not let me do this, actually. It might not let me do this. Oh, it does! Okay, great. Cool, that seems reasonable. So there we go. Now we can, I guess, update and add shapes in if we want to see shapes, if we don't care about shapes. What's the... Is it the pound symbol? So shapes and colors. colors only. So our dataset consists of continuous predictor variables, but we may often be working with categorical predictor variables. Okay, so this was a question that we had earlier. The KNN algorithm can't handle categorical variables natively. They need to first be encoded somehow, or distance metrics other than Euclidean distance must be used, or maybe both too, right? It's also important to scale the predictor variables by dividing them by their standard deviation. This preserves the relationships between the variables, but ensures that the variables measured on larger scales aren't given more importance by the algorithm, right? So standardization, I have heard that that's quite important. So in the current example, if we divided the glucose and insulin variables by 1,000,000, then predictions would rely mostly on the value of the SSPG variable, because it'll be the largest, I suppose. We don't need to scale the predictors ourselves, because by default, the KNN algorithm wrapped by the MLR package does it for us. Okay, well that's great news. Okay, so using MLR to train your first KNN model. The no insulin production one only happens genetically, or damage sustained to the pancreas. Oh, okay, interesting. I didn't know that, Martin. So we understand the problem. Now we need to train the algorithm to build the model. Building a machine learning model with the MLR package has 3 stages. Define the task. The task consists of the data and what we want to do with it. In this case, the data is the tibble that we created, and we want to classify the data with the class variable as the target. Yes, that makes sense. Define the learner. What? The learner is simply the name of the algorithm we plan to use, along with any additional arguments the algorithm accepts. And then to train. This stage is what it sounds like. You pass the task to the learner, and the learner generates a model you can use to make predictions. Okay, so 3 stages for the MLR package. Define the task, define the learner, train. Seems reasonable. So let's begin by defining the task. The components needed to define a task are the data containing the predictor variables, the variables we hope to contain the information to make predictions. So that's going to be our glucose, insulin, and SSPG. The target variable we want to predict, which is the class variable. For supervised learning, the target variable will be categorical if we have a classification problem. Yes. And continuous if we have a regression problem. Right. For unsupervised learning, we omit the target variable from our task definition as we don't have access to labeled data. Got it. All right, so here's what we're looking at. We're going to input the glucose, insulin, SSPG, and our target's going to be the class, right? We want to build a classification model, so we use the make class if task function. Make class if task. When we build regression and clustering models in parts 3 and 5, we'll use make regression task function and make cluster task. Okay, cool. Seems reasonable. We supply the name of our tibble as the data, and the name of the factor that contains the class labels as the target. So diabetes task. Okay, so we're actually going to... So this is going to give me some kind of output then, because we're labeling this as... well, as output from this function, right? So this function outputs something, and I'm going to label it as diabetes task. Make class if task. Data is our tibble. Target equals class. Okay, cool. That seems reasonable. Can I highlight you at all, please? Hello. Okay, let's do some classification. Let's see what happens. So make class if task. It's a long title. So our data is the diabetes tibble, and the target is the class. So we have to wrap the target in quotations, apparently. Okay, what kind of warning in make task? hence it will be converted. I don't know if that is good or bad. Okay, I got a list of 6. Okay, I have no idea what to do with this list, but we got some kind of output. We got a list of 6 things as an output. You may notice a warning message from MLR when you build the task stating that your data is not a pure data frame, right? We did convert it to a tibble. This isn't a problem because the function will convert the tibble into a data frame for us. Okay, cool. So that's what that warning is about. If we call the task, we can see it's a classification task on the tibble whose target, yeah. We also get some information about the number of observations and the number of different types of variables, often called features. Right, some additional information includes blah, blah, blah. Okay. Wait, was this? Yeah, okay, so this must have all been in here? Oh, I see, yeah, so... Oh no, maybe I can't see some of this stuff. Where is this? I guess I could just type it into the script. Okay, so that's where they're getting all their business. So class of class observation features, numeric, blah blah blah, 3 classes. Okay, so that's where they're getting all of that information. So that's just the setup, right? That's the setup telling it that we're going to do a classification task. Now let's define our learner. The components needed to define a learner are as follows. The class of algorithm we're using. Class if for classification, regression, cluster, serve, multi-label. Okay. Algorithm that we're using. Oh, hi, Dr. Zach. Happy Friday to you too. The Canon model. Boom. There's the Canon model. I haven't played Celeste, but I've heard that's quite good. How are you doing today, Zach? Happy Friday, by the way. Thank you for the well wishes. So I lost my train of thought. Okay, the class that we need to define the learner. The components needed to define the learner are the class. So ours is going to be classification. The algorithm that we're using, I assume, is KNN, and any additional options. Okay. As you see, the first and second components are combined together in a single character argument to define which algorithm will be used. Classif.knn. Okay, so it's a dot blah blah. Okay, yeah. The components of the learner, that makes sense. We use the makeLearner function to define a learner. The first argument is the algorithm that we're going to use to train, so we're going to use classif.knn. The argument par.vals stands for parameter values, which allows us to specify the number of k nearest neighbors we want to use. For now, we'll just set this to 2, but we'll discuss how to choose k soon. Okay, cool. So we're going to, I have no idea what the output's going to be. Our last output was a list. Let's get rid of that. We don't need that. Boop. So what was our first step? So the first step wasn't, I should probably be a little bit better at how I like label some stuff. So what we're actually doing is we're actually defining the task. And then we're defining the learner. Let's run that. Okay, so KNN comes out as a list as well. in case you're curious. So it comes out as a list of 15. We could take a look at it, I suppose, if we wanted to. KNN, that'll pop us down here. So learner classif.knn from package class. Name k nearest neighbor. Yeah, properties to class, multi-class, numerics, predictive, hyperparameters k equals 2. Okay, so it doesn't really give me an outrageous amount of information, but there it is. Can you get Reese's autograph for your book? Sure. Sure. What's the easiest way to get that to you? Yeah? You're gonna be famous? Are you gonna be famous? You're gonna be famous puppy?
Look at
You're gonna be
me!
famous puppies? I need to get a mat remover for you. You got a big mat back here. It's probably bugging the heck out of you. Right? His currently has his gigantic head on my arm right now, Zach. I'm sorry. Okay, lay down. Lay down. Lay down. Lay down. There you go. How to list all of MLR's algorithms. I don't really care about that. I can look that up on ChatGPT. Putting it all together. Okay, so now that we've defined our task and our learning, we can now train the model. Woo, I'm so excited. Our first KNN model. The components needed to train a model are the learner and task we've defined, right? So we defined, what is it, diabetes, task, and KNN as our task and learner. So I imagine those are the things we're going to need to pipe into the model. So the whole process of defining the task and learner and combining them to train the model is shown in figure 3.8. Okay, the learner, the task. This is achieved with the train function, which takes the learner as the first argument and the task as its second argument. Okay, so that seems relatively straightforward. Train. I wish I had like a little train choo-choo. So KNN model. We're going to train KNN, comma, diabetes task. Okay, so that looked like it worked out. We have our model, our list of 8 popped out over here. There's a lot of sub things in this. It's a list of 8, but there's a lot of stuff in there. Okay, so we have our, so let's pass data through it to see how it performs. The predict function makes unlabeled data and passes it through the model to get the predicted classes. The first argument is the model, and the data being passed to it is given as the new data argument. What? It's just going to pass the original Tibble into it? What? Shouldn't we give it new data? I guess we can check that it reasonably does stuff. This feels weird. We can pass these predictions as the first argument of the performance function. This function compares the classes predicted by the model to the true classes. So if we're putting in this, wouldn't we expect it to be pretty much 100%? Oh. Let me read more before I say something dumb. This function compares the classes predicted by the model to the true classes, yes, and returns performance metrics of how well the predicted and true values match each other. So we're going to be looking at, so when we pass the Tibble back through, which is our original data, it'll go through the model, and we're going to look to see how often we get a correct flag a correct class prediction. And that's going to be how well the model performs. Is that what they're asking me to do? So we put all the data back into the model to get predicted values. We take the predicted values and the true values and we get some kind of metric. Yeah, okay. Okay. It's weird that I guess I don't really have any other data to really verify, right? I guess suppose what we probably would want to do is we'd probably want to take the original data set and chop it up in some way, right? It just feels weird to use the whole data set to train and then go back and use the data set again to like get our performance metrics. It feels a little shady to me. Training and yeah, we need to verify. It feels a little shady what we're doing right now, but they haven't really talked about doing that with the data yet, I don't think. So we specify which performance metrics we want the function to return by supplying them as a list to the measures argument. Okay, so what have we done so far? We've put the Tibble back in and allowed it to predict using the model. Okay, so we're going to predict using the original data. And for this particular output, which is going to be some list, we're going to feed that into the performance function and get some measures associated with the KNN algorithm. So MMCE, the mean misclassification error, and the ACC, or accuracy. All right, I should probably write that down somewhere. Okay, train, and then we are going to predict using the original data, and then look at performance metrics. I'm going to write MMCE is, what do we say, mean misclassification. Mean misclassification error. And ACC is accuracy. Okay, did we get the same numbers? Probably not. Would our models necessarily get the same numbers? I don't think so, right? Because it's dependent on the output of CAN. It's dependent on the output of our model, right? All right, so we've trained it with a particular thing, and then we've gone back basically to kind of see how well it's worked on the original data set. I have a feeling that our values should be close, but they might not necessarily be the same. Yeah, and this is kind of what I was kind of worried about. Does this mean it will perform? So it's correctly classifying 95.2%, and ours is pretty close to that, 96%-ish. Does it mean it's going to perform well on new unseen patients? We don't know. Evaluating model performance by asking it to make predictions on data you used to train it in the first place tells you very little about how the model will perform. I was worried about that. You should never evaluate model performance in this way. Before we discuss why, I want to introduce an important concept of the bias-variance trade-off. Yeah, Zach, you got it, exactly. We don't know. We don't have a lot of data here, though. It's like, there's only like 145 pieces of data, so I guess we could probably feed in like 100 to train. I think you always want to have a bigger training, right?
Generally, you need at least 3 PIs to approximate the value more accurately. But who needs limits? Embrace infinity.
Over 9,000! Okay, we looked a little bit at the bias-variance trade-off, I think, from James last week. And this is the idea of what is it, like the more flexibility you add, the more you can overfit your data, right? So like there's this idea that like if you try to decrease bias, right? So if I want to decrease the variance, it's going to increase the bias, and vice versa. If I try to decrease the bias, it's going to increase the variance. Is that how it works? But it has something to do with overfitting the data, right? The model was too simple and it was biased towards a misclassifying, right? So if you bias it, you might underfit, which is going to increase the variance in the data. And if you overfit the data, you're going to bring the bias down. The way that James was talking about it was this. Actually, maybe I'll pull the section up that I thought was really interesting. Where was this? Squares. Oh, maybe it wasn't in here. Am I in the wrong one? I think I'm in the wrong one. I was just been kind of looking at some of these other statistical books too, just to try to get a bit more of a statistical background on some of this and how this works. So I remember reading this. Here it is. So the bias variance trade-off. They had a really good visual that kind of helped me see this through a little bit. So they were looking at like splines or spleens or whatever it's called. Well, maybe not. No, maybe not. Maybe I'm just lying to myself. Maybe I just dreamt it last night. I was just dreaming about machine learning last night. So they were looking at mean square error because they've been talking a little bit about regression in the James book. And so they're saying, so through beyond the scope of the book, it's possible to show that the expected mean square error given the value, or this, so x naught will be kind of like a new data point that we don't really know what the output looks like, can always be decomposed into the sum of 3 fundamental qualities: the variance of the model evaluated at that new data point, the squared bias of the model evaluated at that data point, and the variance of the epsilon term, which is always kind of like the inherent difference. I think, or if I remember correctly, it's kind of like the inherent difference between, it's the error that we can account for based on the model that we're what's the word I'm looking for? Like, we create the model. It's a what's the word? What's the word, chat? What am I looking for? It's not the true model. It's the hypothesis, not the hypothesized. What's the fucking word? What's the word? A pea hat. What's the hat? What does the hat mean? Yes, the estimated. Yes, it's the estimated. The hat always is the estimated. So this is our estimated model. Okay, so in other words, they're saying that I think they're saying like the expected value here between what the actual output is and the model evaluated at this x naught can be decomposed into these three things. And I think like the idea is that these are the two things that you can adjust. Like we can never really, I don't think we can ever really deal with this part of the equation based on the model that we're using. That's my understanding. I'm happy to be corrected if I'm thinking incorrectly. So the variance and the bias are the two things that we have ability to play around with because we're kind of estimating the model, right? This f hat. Gots to go to 3:30 a.m. Oh, well, I appreciate you coming and hanging out, Martin. So James has a little bit more information, I think, on kind of like the statistical breakdown of what this looks like, in case you guys want to look at it. So that's like it's in chapter 2, and I've just been kind of like leafing through that. So if you want a bit more kind of statistical look at this trade-off between bias and variance, it'll be in the James book, chapter 2. Okay, so blah, 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 blah. Yeah, and then you always get like this really cool, like these really cool, interesting curves. And I think what Reese is going to try to tell us is that, yes, we want to try to find an optimal place where we kind of minimize variance and bias, or sorry, minimize it's not necessarily minimizing the bias and variance, right? Like we can start decreasing the bias to a certain point, in which case if I try to keep decreasing that bias, the variance is just going to like go crazy. So there must be some kind of reasonable estimate that we can make inside this kind of optimal region, right? So the bias, variance, trade-off, generalization, error is the proportion of erroneous predictions a model makes and is a result of overfitting and underfitting. So overfitting means too high bias, right? No, that would be underfitting. So underfitting we get if the bias is too high. And overfitting we get is when the variance is too high. And if either of those things happen, then we can see our total error is really high as well. So the idea is to try to bring down the bias and variance to some degree so that we can kind of minimize the error that we're seeing in the model, I think. I think that's the general, I feel like that's the layman's way of explaining what I think they're trying to get at. So the error associated with overfitting to complex a model is variance. Oh, the error associated with overfitting is variance. Did I have it backwards then? The error associated with underfitting too simple a model is bias. Maybe I have it backwards. I'm just thinking like a regression model. Like I could have a bunch of different data points in a scatter plot, and I could build a linear regression model in two-dimensional space. That's a bias, isn't it? Right? Like I've biased my model to be linear. It would underfit the data. Yeah, okay, so the error associated with underfitting is bias. I think that's what they're trying to say. Or what I could do is I could take my model and literally just go through every single data point and produce like an x to the n kind of curve that goes through every single data point. And then what's going to happen there is when I compare that estimated model to the actual model, I'm going to get high variance, I think, right? Where the linear model probably has a lower variance, because what I'm doing is I'm kind of like going crazy, right? I'm going between all these data points. So that's how I'm kind of interpreting it, right? Like the more complicated your model, the more variance you're going to get with respect to the true f and not the f hat, right? So your f hat's going to have a lot of variance if you give it a lot of flexibility. Okay, now look at figure 3.11. Can you see that the underfit model poorly represents the patterns in the data, and the overfit model is too granular and models noise in the data instead of real patterns? So overfit would be, yeah, literally producing a path through here that puts every single purple on one side and every single green on the other side. Lots of variance, right? In that particular path. If I just do a simple straight up and down path, so I only really look at variable 1, and I just choose some value of variable 1 without really considering variable 2, it's an underfit. And the optimal will lie somewhere in between. So it's a y equals mx plus b in this case. That might be the most useful to help us classify green or purple. So I think what they're trying to say is, like, there's a lot of bias here, right? I've just said x equals some number. So I've put a lot of bias in here. But is it really, does it have high variance? Not really. Well, I guess we're looking at squared distances, so maybe it does have a decent amount of variance. But they're saying that the overfitting is likely to cause a lot more variance between the linear model and this, like, curvy model. I think that's what they're trying to say. Here we go. So the question you're probably asking is, how do I tell if I'm over or underfitting? The answer is a technique called cross-validation. I think this is what we were trying to allude to a little bit earlier, right? So, like, how rather than using that original data set again and getting this, like, 96% output value, right, of, like, accuracy, I want to be able to actually validate that number somehow. Check paragraph 2 of... Okay, we can do that. Paragraph 2. So it says the bias variance dilemma or bias variance problem is the conflict in trying to simultaneously minimize these two sources of error that prevent supervised learning algorithms from generalizing beyond their training set. The bias error is an error from erroneous assumptions in the learning algorithm, and a high bias can cause an algorithm to miss relevant relationships, right, underfit the data. The variance is an error from sensitivity to small fluctuations in the training set. That's how the variance ties into play here. Got it. Okay. Sensitivity to small fluctuations in the training set. High variance may result from an algorithm modeling the random noise in the training data overfitting. Yeah. Right, so we want to have a little bit of that noise and not overfit to that noise. No, I think that helps me understand, I think, what the variance is trying to describe. It's trying to describe the fluctuations in the training set, right? So if we're moving stuff around too much based on small fluctuations in the training set, we're probably overfitting the data, is what this is, I think, trying to tell me. Okay, how are we doing? 12:30, not too bad. Maybe we can actually get through some cross-validation before we sign off for the day. So using cross-validation to tell if we're overfitting or underfitting. Okay, so we typically split our data in two. We use one portion to train the model, called the training set. We use the remaining portion, which the algorithm never sees during training, to test the model. Yes. So I have heard of this. This portion is called the test set. We then evaluate how close the model's predictions on the test set are to their true values. Right, so those performance metrics, we probably just use them like we would, but we're using them on the test set rather than the original training set. So we summarize the closeness of these predictions with performance metrics. Measuring how well the trained model performs on the test set helps us determine if the model will perform well on unseen data. Right. So this process is called cross-validation and is an extremely important approach in any supervised machine learning pipeline. Once we have cross-validated our model and are happy with the performance, we then use all the data we have. Wait, once we have cross-validated our model and are happy with its performance, we then use all the data we have, including the data in the test set, to train the final model. What? Because typically the more data we train our model with, the less bias it will have. Okay. There are 3 common cross-validation approaches. Oh my gosh. Hold out, K-fold, leave one out. Let's start by reminding ourselves of the task and learner we created. Right, so we have the diabetes task, we have the KMN, which is our learner. Before we train the final model on all the data, let's cross-validate the learner. Ordinarily, you would decide on a cross-validation strategy most appropriate for your data, but for the purposes of demonstrations, I'm going to show you hold out, K-fold, and leave one out cross-validation. Cool, okay. I've only heard of K-fold. So you want to see if the model has any... Yeah, exactly. So I'm assuming cross-validation is going to help us understand the predictive power, right? So hold-out cross-validation is the simplest method to understand. You simply hold out a random proportion of your data as your test set and train your model on the remaining data. You then pass the test set through the model and calculate its performance metrics. You can see a scheme of hold-out cross-validation in 3.12, right? So you choose some proportion as the training, some proportion as the test. We train the model only on the training. Predictions are made on the test set. And then we compare them with the true value, because we actually know the true values of this particular data in the test set. So we can make a comparison and use that as our performance metric evaluation. Yeah. It's like having a practice test and real test questions. Yes, I get it. I get it. So holdout CV doesn't seem too bad. We just have to understand what proportion might be helpful. When following this, you need to decide what proportion. You need to decide what proportion of the data to use as the test set. Yes, the larger the test set is, the smaller your training set will be. The larger the test set, the smaller the training. Yes. Here's the confusing part. Performance estimation by cross-validation is also subject to error. Right, if your test set is too small, then the estimate of performance is going to have high variance. But if the training set is... What? If the test set's too small, the estimate of performance will have high variance. But if the training set is too small, then the estimate of performance is going to have high bias. Wait. Let me read that once again. So if your test set's too small... So that's the stuff we're backfilling into the output, right? To classify. Then the estimate of performance is going to have high variance. But if the training set is too small, then the estimate of performance is going to have high bias. So if the training set's too small, the model's probably going to be too simple, is what they're saying, and have high bias. So we need to make sure we have enough data in the training set to minimize that bias to some extent. And they're also saying if the test set is too small, oh, I see, then our estimate of performance is going to have high variance. Got it. Yeah. So the metrics that we get could potentially have high variance. What do you want? What do you want? What do you want? Are you hungry? You want food? You want foodsies? You hungry? I'm kind of hungry too. It's about time for lunch, isn't it? It's almost time. This is the only time I've been able to stream this week. Can you relax for 20 minutes? Can you give me 20 minutes? I will pay so much attention to you in 20 minutes, you're going to hate me for the rest of the weekend. How does that sound? 2/7 versus 3/7 is very different, but 2 100ths and 3 100ths is not really. He's so needy right now, fam. It's crazy. He's usually just like passed out on the couch till like 3. He usually wants a walk around 3 o'clock, or he wants to just kind of like, but it's really early for him today. So a commonly used split is to use 2/3 of the data for training and the remaining 1/3 as test. But this depends on the number of cases in the data, among other things. So commonly using a 66.6 to 33.3 ratio. All right, so the first step when employing, also, I guess we have to choose stuff at random too, don't we? So we have to make sure that we don't choose all of the same class, for example, to do the test set, right? So we really do, I think, have to figure out how to sample this properly. So the first step when employing any CV NLR is to make a resampling description, which is simply a set of instructions for how the data will be split into test and training sets. The first argument to the make resample description function is the CV method we're going to use, in this case, holdout. Okay, method holdout, split equals 2/3, stratify equals true. So what does that mean? So the split I get, right? So the split's going to be the 2/3 rule, I guess, that Reese is telling us to use here. So I've included an additional optional argument, stratify equals true. It asks the function to ensure that when it splits the data into training and test sets, it tries to maintain the proportion of each class of patients in each set. Beautiful. Okay, that's what I was worried about, making sure that we got a relatively close sample for the test set, right? We want that population to be relatively similar to the entire population, right? So this is important when groups are very unbalanced. Yeah, I know there's some strategies when working with like unbalanced groups, like if you're looking at like who's going to default on a loan and it's very like you have very small amount of data on the people that do. And there's ways to work around that, but I think hopefully we'll deal with that later. Okay, so let's try to do a holdout CV, and then I'm probably going to call it a day. So now that we've defined how we're going to cross-validate our learner, we can run the CV using the resample function. Okay, do I have to do something up here? Yes, I should probably do this. How am I going to... I'm going to put a star here, because that was with the original data. And then what we're doing now is we're kind of looking at a holdout method for cross-validation. Okay, so we can toss that in. Holdout came out, that looks fine. Hello? Okay, so there's a resample function. We supply the learner and the task that we created. Okay, and the resampling method we defined. Okay, to the resample function. We also give it, ask it to give the measures. I see. Okay, so the same 2 measures we were using before. Cool, okay, so this is great because now I actually like have a reasonable amount of code that I can use. I have a script that I can actually use, which is really, really cool. Okay, so we have a MMCE, so what is that? A mean misclassification error of 12% and an accuracy of 88%. The accuracy, yeah, we'll notice 2 things. The accuracy of the model as estimated by holdout cross-validation is less than when we evaluate its performance on the original data. Yes, your performance metrics will probably be different than mine. In fact, run the resample function over and over again and get very different results each time. The reason for this variance is that the data is randomly split into the test and training set. Sometimes the split is such that the model performs well. Sometimes the split is such it performs poorly. Let's finish off today with this exercise. Use the make resample description function to create another holdout resampling that uses 10% of the data as the test set and does not use stratified sampling. I think we can do that. So I need to write a couple of things in here. So this is, hold on, cross validation. I wanted to put a note in here. So the split gives 2/3 to training, right? And then 1/3 to test. Stratify equals true. Ensures, what's that? That the sample population is roughly in the same proportion as the, so sample is roughly same proportion as population. Okay, I don't think this example is like super hard. All we're really doing here, oh, I have to actually do this one more time too, don't I? So this would just be like, we're not overwriting, we're just going to call it like 2. So the method can still be hold out the split now. What did they want the split to be? They wanted it to be 10% of the data as the test set. So we used 1/3, so 33%. They want, so we want 9/10 then. 9/10 to be the training. And then this can be false. This is going to be terrible, right? Like, not stratifying and using such a small test set is probably going to really drop our numbers down, won't it? Okay, so KNN task, hold out 2. That seems okay. And accuracy is 80%, which is actually quite surprising. Okay. I thought it was going to be much lower than that. It's still fairly accurate, to be fair. What do you mean you're not? What does that mean? You're not supposed to run it more than once? You mean I'm not supposed to just keep doing it until I find a really great accuracy? I'm not supposed to cook the books. P-hacking, yes, that's the phrase. That's the phrase I was looking for. Exactly. Exactly the phrase.
Another one. Another one. Another one.
Just keep going until you get a really great accuracy. Okay, I'm going to save this in my machine learning section. What should we save this as? This is a KNN script. Boop. Sweet. So I guess when we come back next Friday, we'll just kind of keep on keeping on with Chapter 3. Oh God, what's happening? Why is it doing that? Please stop. No, stop. No, how do I fix this? How do I can't fix it. Sad. So where did we actually get to? It's using the, oh God, it's just so frustrating. I need to close this before I lose my mind. Okay, please, hopefully you reset to scroll properly. Why is it doing that? Why is it doing that? I don't want that to happen. No. Okay, it's working properly here now. Okay, great. It's working properly here now too. Cool. All I had to do is mash my keyboard. Mashing the keyboard fixes everything. When in doubt, mash the keyboard. So we got through, we're kind of in, no, we're in 3.5, I think, right? So we're doing a pretty good, we've done a pretty good chunk today in a couple hours. We're on holdout. We'll probably do the other validations, I think, on Friday as well. And there we go. And then tuning K to improve the model. I'm kind of curious about 3.7 as well. So with that, I think I'm going to sign off. Let's see, is this the James text or is this the other text? This is the James text. So I might also read a little bit in the James text just to get a bit more of a kind of stats background on kind of what's happening. So I'm probably going to read through chapter 4 a little bit. And just kind of see if there's anything in here that might be interesting to chat about and put into the chat. So yeah, so I think I'm going to kind of call it here. We'll have some more chat, so there's a bit of a chat happening here in the Machine Learning General 2025. If you need the resources, they're linked here in the forum. So Reese is the one that we're kind of working through so I can kind of get a better sense of how to do some of this stuff in R. And then I'm using James as kind of a supplement to kind of understand a little bit more of the statistical background of stuff. So in James, I'm kind of doing this off the side of my desk, but I've been kind of just reading through chapter 3. And I think I'm pretty happy. I mean, it does an introduction to R. I'm not going to read that. So I'm probably just going to start kind of leafing through chapter 4. And if there's some stuff in chapter 4 that I'm kind of curious about or I'm not really sure about, I might post that in the chat. I know that also inside the chat, I think it was QK had some questions from the James text. So if anyone has some potential answers to these, or like some or all of these, feel free to help them out, because I probably won't get to regression until we get there in Reese, which is a little bit later. Hi Zach Sparrow. Oh, nice. Maybe you press the small button between. Oh, maybe. That could be true. Yeah. All I know is when in doubt, I just like mash buttons around until something fixes itself. Literally had to do KNN for the first time. Oh, that's really cool. That's really cool. Yeah, this is kind of my first crack at it, like using R, right? Like I've never actually gone through the procedure of how to construct a KNN model in R. So this has been really helpful for me to kind of see the process and the procedure and how it works. So I've really, really, really liked that. Maybe eventually we'll get to random forest and XGBoost. I think those are more, is that tree stuff? Where you're looking at the classification trees? Where you don't necessarily know outputs? I can't remember. Did in Python? Yeah. So, I mean, if you have some, if you're a part of the Discord channel and you have some Python scripts that you're willing to share with us, specifically around kind of which packages might be beneficial for people to work with. I know there are some individuals like Tyrion that wants to kind of understand how this is done in Python. I probably don't have enough time to do it in Python. But yeah, if you're in the Discord and want to toss some of that stuff into like the machine learning resources, like the packages that you use and some of the scripts in Python that might be helpful, I'm sure people would love that. There's probably equally as many people that that want to do this in Python as in R. So, well, actually, I lied. It's probably more people that want to do this in Python than in R. But the book is in R, and I'm comfortable with that lingo. So, anyway, thanks everyone for coming and hanging out today. It was a good session. I feel pretty good so far about KNN. I feel like it's the book has guided me in a way that hasn't really answered a lot of my statistical questions about how things work in the background. It's done enough, I think, to motivate how the algorithm works. So I'm hoping that James will illuminate a little bit more of the statistical background on how this is all kind of coming together and working. Right now, I feel like everything's kind of in a bit of a black box, right? I'm kind of feeding some information into this MLR package, and it's giving me an output that seems reasonably okay. So I still I'd still like to learn a little bit more of that background stuff. What about C++? No. Is the book in Discord? Yeah. Actually, I'll pop back over into here so you can see. So if you're in Discord, you will need the online classes role. So you just have to go into channels and roles and click up here at the very top. It just says, please give me the role. That's going to give you the online classes role. Once you have that, you should be able to find the machine learning channel and just go into the forum. And so far it's the only post in the forum, and people have just been sharing resources inside that forum post. So if you need help finding that, just tag me and I can help you find that. But for now, I think I'm going to go ahead and end off stream. And I will be back next week on Friday. So that'll be July the 4th. I'll be here. That's not a holiday in Canada. I realize that might be a holiday in the United States, though. That might be Independence Day. But I'll be kicking around Friday morning if you're not off with the family doing family-oriented things. Trying to finish off some classification stuff. I will not. That's okay, Zach. I understand. That's a very big family day, a family-oriented day in the U.S. So you can catch the VOD. So VODs are going to be available on Twitch, obviously, and then I'll be posting them to YouTube when I get a chance as well. So I'll see y'all next Friday for sure, and hopefully I'll get a chance to get some gaming streams in between now and next week too. So until then, take care, everyone. Have a good rest of your weekend. Goodbye!